Welcome to lesson 2 on bonding. In this lesson, we took 6 unknowns and we performed various forms of qualitative analysis to try and figure out what we had. We looked at the color and the texture, the melting point, the solubility in water. We use water as the polar solvent. The conductivity, its ability to conduct electricity as a solid in water, and determine the bond types. So I'm not going to repeat all the observations that we had, but let's take a little bit of a deeper look at the types of chemical bonds. We drew some basic structures in class, but let's look in closer now at those properties. So we're going to talk first about ionic compounds, and we're going to look closely at sodium chloride, your typical table salt ionic compound example. If you draw the electron configuration for sodium out, you end with S1. That means sodium has 1 valence electron. If you do it for chlorine, you end with S2P5. That means chlorine has 7 valence electrons. It's got this 1 empty spot. Now, chlorine has a much higher ionization energy than sodium. It's much more to the right in the same column, same row. Okay. We're going to call ionization energy electronegativity. Chlorine pulls on that electron and we get your typical ionic transfer. Okay. And what results is sodium that has 1 empty shell, leaving it with a +1 charge, and chlorine now that has a full octet of electrons and owns that transferred electron. It's now -1. Now, you never just have one sodium chloride compound. You have this large crystal lattice, we'll call it. And it repeats moles and moles of times here, but I'm just going to draw 2 units for now. So this we refer to as the ionic lattice. Now let's look at a different example. If we draw the electron configuration for magnesium, that ends with S2. It's got 2 outer valence electrons. I'm using these dots to denote that. And let's also now look at sulfur. Okay. Sulfur ends with S2P4. It's got 2 + 4 or 6 valence electrons. Okay. So unlike chloride, sulfur has 2 empty spots. It has a much higher electronegativity than magnesium because it has a much larger nuclear charge. So it completely yanks those electrons from magnesium. We get an ionic transfer, and we get a repeating crystal lattice of magnesium and sulfide ions. Remember, this occurs much more than just twice, but twice is good enough. So if you look at this, according to Coulomb's law, magnesium sulfide here is going to have the higher melting point. And that's because they are both in the same column. Sulfur and chloride have a similar radius. Sodium and magnesium have a similar radius. But there is a larger Coulombic attraction between magnesium and sulfide. Okay? And you can think about the reverse situation. If we had something like lithium fluoride and we compared it up here to sodium chloride, lithium and fluoride and sodium and chloride all have a +1, -1 attraction. But lithium, in this case, is a smaller ion, and fluoride would be a smaller ion. That lattice could pack tighter, and according to Coulomb's law, there would be a greater Coulombic attraction, and thus a higher melting point. So in an ionic compound, Coulomb's law determines the melting point. We also talked about polar covalent compounds, and a typical one we like to talk about is hydrofluoric acid. So hydrogen's weird, it just has 1 valence electron. It's actually the only atom that's trying to be like helium, which is up here, kind of strange. Fluoride is trying to be like neon, so it's got its 7. Okay. Now, the electronegativity difference between hydrogen and fluorine is not great enough for a transfer. So what happens is we get a share of these electrons. So if you notice, hydrogen's got what it needs. It's got those 2 electrons to be like helium. And fluorine has what it needs. It's got those 8 electrons to be like neon. But what we have here is a covalent sharing of electrons. Now, in reality, fluorine has a much higher electronegativity than hydrogen. So those electrons, although they're shared, are much closer to fluorine. Okay, so it looks more like this. And that's what is meant by a partial negative. It's not a full negative like the chloride and oxide or sulfide ions in the previous example, but it's a partial negative because they are closer to fluoride. And conversely, that's going to be a partial positive. And this is your polar bond. Notice that it's pulled closer to fluorine in this case, and we often use this arrow to show which atom in this case is pulling on those electrons tighter. So a polar bond is a non-equivalent or an unbalanced sharing of those electrons. So the way this is going to be seen when you draw it is you're going to draw a line and you're going to put a partial negative on that fluorine and a partial positive. So because of that, when we have another one, they line up so that these dipoles here, that's called a dipole, interact. And we get this region in between here, which we called an IMF force, okay, intermolecular force. Now, when this boils, remember this one and this one separate. We don't break that bond right there. So a polar covalent compound has dipoles, which means an unequal sharing of that electron, because the fluorine is simply pulling harder. Think about it as a game of tug of war, and fluorine won. Okay. Let's stick with fluorine though, and go to a non-polar covalent compound. And if we had two fluorine molecules together, the fluorine dipole, or a diatomic molecule. So both of these are going to have their 7 valence. Okay, 2, 3, 4, 5, 6, 7. But if you notice, if it's the same element, they have the exact same electronegativity. So they're going to share that electron, and that is a covalent share, but it's a non-polar share, because when it's all said and done, they are sharing it equally. Okay, so when you get those next to each other, there are no dipoles here, so the intermolecular force is much, much weaker. Now, why you actually have an intermolecular force is something that's semi-complicated, but we'll talk about that next cycle. I have these diagrams up here. This is actually nitrogen, which is a nonpolar molecule as well, liquid nitrogen. So in a nonpolar covalent molecule, unlike the polar, you have an equal overlap or sharing of electrons. Therefore, we have no dipoles, and in this case, a fairly weak intermolecular force. Now, in that network covalent compound, it's pretty simple here. What you're looking at is diamond and graphite, both versions of carbon here. And what you see is just covalent compounds here. Okay. Now, graphite is different because what we have are these 2D layers, and diamond is actually 3D. And this is what allows graphite to be a little bit more malleable than diamond. These layers can slide past one another. It's kind of hard to see right now, but if you notice, you have these regions on the end here where carbon is only having 3 bonds. And those regions of electrons that don't have the 4th bond it needs are what allow these graphite regions to interact with one another. And it's also why graphite is going to be a semiconductor of electricity, because we have these electrons that are moving just a little bit around. So in reality, there are subtle intermolecular forces in graphite, but not many. We mainly have these layers that are packed on one another. They can move back and forth because it's like these 2D stacks. But it's really important to notice that what we have are covalent bonds here. Diamond is a horrible conductor of electricity, whereas graphite is a subtle conductor of electricity due to these carbon atoms here that are missing one bond and have a free electron. Okay, so the network covalent is going to have the highest melting point, and we really only see this with elements of, or compounds of carbon and compounds of silicon who have 4 valence. Remember that 4 valence gives it a lot of bonding flexibility. The last type is metallic compounds, and what's very interesting about metallic compounds is it's this huge compound made out of just one metal. Up here we see gold, okay? So you can imagine this is nothing more than moles and moles and moles of gold. And what it really looks like is the atom itself. Now these are not ions. Let's think about that as the proton of the metal and these as the electrons. But what's really great is these electrons swim around all these different nuclei, and that creates that sea of electrons that we were talking about. Now, depending on the ability for these electrons to move, the metallic bond is either stronger or weaker. We see some interesting characteristics. If we look at gold specifically, it's very malleable. So what that means is these electrons create a very strong bond because they're overlapping all over the place. But because these atoms here aren't really connected, they can slide past one another. And we get what's called malleability, or the ability for the metal to be hammered like a piece of foil or bended. This malleability feature actually also increases when most metals are heated. It's what allows us to pull pieces of copper into a wire. That's actually called ductility, which is similar to malleability. So it's really interesting. These sea of electrons increases the strength. It allows the metal to be very strong. But because the atoms actually aren't physically connected to one another, they can slide past one another, and we are granted this malleability characteristic of metals. Okay, well, you're probably thinking, what about metals that aren't malleable? And that's when we get to something called alloys. So I want you to take your time, because this is a very highly tested topic on the AP test. So what we have here is steel. And steel is what we call an interstitial alloy. Okay, and I'm going to have you know this. Okay. And it's an interstitial alloy because it looks like this. So steel is basically a bunch of iron atoms. Okay, I'm going to draw a very simple alloy here. I'm just going to draw 6 atoms. Okay. Actually, just to make the point, I'm going to draw 9 because I feel like it. Okay. And it's interstitial in the sense that these regions are called the interstitial spaces. And smacked in these regions are little carbon atoms. Okay? So we did not remove any iron atoms. We just snuck some carbons, which are a much smaller atom, in these interstitial spaces. So now when the iron atoms try and slide past one another, they hit these carbon atoms and the malleability decreases. But because oxygen from the environment can still react with the iron, we get this rust that forms. So steel is highly corrosive, but not that malleable due to the presence of those carbon atoms in the interstitial spaces. Okay. Another alloy is brass in this case. Okay. So again, brass looks a lot like copper because it is. Okay. It's got a ton of copper mixed in. It's mainly copper, but it's not all copper. Okay. Substituted in other places where copper atoms would be, we have zinc, which is a slightly smaller atom. And unlike steel, this is called a substitutional alloy. And it makes a lot of sense. Instead of sticking the zinc in the interstitial spaces, we substituted copper atoms with zinc, and this decreased the malleability as well. Now, because it's mainly copper, we still get that copper color. And I should also note that these things are still metallic bonds. So we have this sea of electrons flying around that's reflecting light, which is why we get this shiny surface to most metals. Okay. Now, there is a combination of the two, and that's stainless steel. Stainless steel is a combination of the interstitial steel alloy, okay, and I'm going to leave a space right here to draw a different atom, okay. So it's mainly iron, okay, and it's got the carbon snuck in here, so it's interstitial to keep it really strong, okay. But it's got some out here. Let's see if I can get a different color. I don't have a different color. It's got some chromium, and the chromium forms chromium oxide, which isn't a rust, and keeps the rust from diffusing in the inside. It's kind of complicated, but really the chromium is what keeps the steel itself from rusting, hence we get that stainless steel. So it's interstitial because the carbon atoms are stuck here in the interstitial spaces, but it's substitutional because the chromium atoms have been substituted in replace of the iron. So stainless steel is a great example of both. Really a good one for you guys to understand, both interstitial and substitutional. But all these alloys have that sea of electrons flying around, so they're great conductors of electricity, and they're a very, very, very strong bond. The alloy's main purpose is to decrease that malleability. Okay, so your multiple choice question, press pause and answer this. It says, based on the data in the tables above, which of the following statements provides the best prediction for the boiling point of sodium chloride? So before you do this, replace boiling point for melting point and go back to your notes on the Coulombic attraction in the ionic lattice. Thanks a lot.